In this video, we will solve a classic open-top box optimization problem where we find the size of the cut that maximizes the volume of the box. If you appreciate the content, please give it a like. An open-top box is made by cutting out a square from each corner of a 24-inch by 24-inch piece of paper and folding up the sides. Find the size of the cutout that will maximize the volume of the box. Let's define the size of the cut as x by drawing x into the picture like this. When you fold up the flaps, this length x becomes the height of the box as well. We are going to need an expression for the side length of the folded box. That length appears in the pre-folded diagram right here. Since the pre-cut paper is 24 inches wide and we are making two cuts of length x on either side, the remaining flap has a length of 24 minus 2x. It's the entire length of 24 inches minus the two cuts. And this is a square, so that length of 24 minus 2x appears on either side. Most optimization problems involve a primary equation and a secondary equation, where the primary equation is the quantity you are being asked to maximize. So let's think about what the primary equation would be. We are being asked to find the size of the cutout, in other words, the value of x, that will maximize the volume of the box. Since we are trying to maximize volume, we need to write an equation for volume, which would be our primary equation. So we know the volume of a box is length times width times height. So these two quantities, the length and the width, are the same. So we can say 24 minus 2x times 24 minus 2x would be 24 minus 2x squared, and then times the height, so times x. This is an expression for volume. Normally we would need a secondary equation because the primary equation would involve two variables, and we would use the secondary equation to do a quick substitution and rewrite with one variable. However, in this problem, the primary equation already has only one variable, so we don't actually need a secondary equation. So we just need to maximize this. Before we go on, let's figure out the domain implied by the context of this problem. Remember, our variable x represents the size of the cut. So what's the lower limit for the size of the cut? How small can the cut be? Well, you can't have a cut of size 0 because you would just have a flat piece of paper and no box could be made. So that's the lower boundary. X cannot be 0. It has to be greater than 0. Now, what's the upper limit for how big this cut can be? Well, the entire paper only has a length of 24. So it would be tempting to say, well, x can't be as big as 24. And that's true. X does have to be less than 24, but there's a smaller number that's actually the limit. Can you guess what I'm talking about? There are two cuts being made. We are cutting in from the left and we are cutting in from the right. So a cut of 12 would cut halfway into the paper from both sides and the whole thing would fall apart. I mean, actually we're cutting 4 corners. So if you cut 12, you would just be cutting this piece of paper into 4 pieces that would then fall on the ground. So your cut cannot be 12. It must be smaller than 12. So this is the domain implied by the context of the problem. X must be between 0 and 12. Our strategy is to make a v-prime sign chart and use that to find the value of x that maximizes the volume. So let's take the derivative of the volume expression. This is a product, so we are going to need the product rule. We have the yellow function and the blue function. So according to the product rule, we sort of go through this twice. The first time through, we take the derivative of the yellow function, which is 1, and we leave the blue function unchanged. So that's 24 minus 2x squared, and then we put a plus. Then we go through it again. The second time through, we leave the yellow function unchanged, and we take the derivative of the blue function. This is going to require the chain rule. So the derivative of the outer function is this, and the inner function is 24 minus 2x. But then the chain rule demands that we multiply by the derivative of this inner function, which is negative 2. Let's simplify this a little bit. Multiplying the x and the 2 and the negative 2, we get negative 4x in the front. Ultimately, we need to find where v prime equals 0 in order to make the v prime sign chart. In this form, it would be a little bit difficult to find where v prime is equal to 0. So let's simplify by factoring out this common factor involving 24 minus 2x. I see this base of 24 minus 2x showing up in both terms. So we should be able to bring that outside of parentheses. Think GCF, greatest common factor. So 24 minus 2x is going to be out in the front of some parentheses. However, what will the exponent be? Well, you always use the lower exponent. So obviously we have the exponent of 2, and this is like an exponent of 1. So we're just going to bring out the 1 factor. We can think about what goes inside the parentheses, what's sort of left over after you factor this out, by picturing division. Normally we do this in our heads, but I'm showing it for instructional purposes. If we divide each of these terms by the common factor we are factoring out, that will tell us what will be left behind inside the parentheses. So for this first term, 1 factor of 24 minus 2x cancels out one of these factors, leaving 1 factor behind. So we still have a factor of 24 minus 2x from the first term. From the second term, there's only 1 factor of 24 minus 2x, so these cancel out, and that just leaves minus 4x. So we can now combine these like terms. So we have v prime is equal to 24 minus 2x times 24 minus 6x. We can easily find where v prime is equal to 0 now by setting each of these factors equal to 0. If we set 24 minus 2x equal to 0, adding 2x to both sides, we get 24 is equal to 2x. And dividing both sides by 2, we get x is equal to 12. If we set the second factor equal to 0, that's 24 minus 6x is equal to 0. Adding 6x to both sides, we get 24 is equal to 6x. And dividing both sides by 6, we get x is equal to 4. Don't forget about the domain limitations implied by the context of the problem. We determined that x has to be less than 12 because we only have 24 inches of paper to work with, and we are making 2 cuts. If we cut 12 from the left and 12 from the right, those cuts will meet in the middle and the paper will fall apart, and you can't make a box. So x must be less than 12. Since x cannot equal 12, this is not a valid solution. This is not a critical value. So when we make the v prime sign chart, we will only have the 1 critical value. Set up your v prime sign chart, including the endpoints of your domain, the 1 critical value, and a row for every factor of v prime. Make sure to label your sign chart as v prime. we need to determine whether these factors are positive or negative in each interval. Remember that 24 minus 2x is equal to 0 at x equals 12. So this factor is equal to 0 right here. This is the only place where this factor might change signs. That means there will be no sign change on the interval from 0 to 12. No sign change on this domain. It'll either be negative in both intervals or positive in both intervals. If we were to plug in 4, we would get 2 times 4 is 8, and 24 minus 8 is a positive number. So using that as a test value, this factor is positive in both intervals. 24 minus 6x is equal to 0 at x equals 4. So this is the only place where this factor might change signs. So let's use 2 as a test value. This would be 24 minus 12. That's a positive number. So this factor will be positive in this interval. Let's use a test value of 5 for this interval. If we plug in 5, that's going to be minus 30. 24 minus 30, that's a negative number. So the overall sign of v prime is positive from 0 to 4 and negative from 4 to 12. Normally, we would say v has a relative maximum at x equals 4 because v prime changes from positive to negative. But relative maximum is not good enough. We are trying to maximize the volume. We need to know that the volume has an absolute maximum at x equals 4. Luckily, this is a special case. Because volume only has one critical value on its domain, we can actually use this sign chart to conclude that v has an absolute maximum at x equals 4, not just a relative maximum. Since there is only one critical value, it divides the entire domain into just two intervals. Since v prime is positive on the first interval and negative on the second interval, that means the volume is increasing on the first part of its domain and then decreasing for the second part of its domain. That means there is an absolute maximum at x equals 4, not just a relative maximum. Instead of saying v prime changes from positive to negative, which would only give us a relative max, not an absolute max, we say v has an absolute maximum at x equals 4 because v prime is positive from 0 to 4 and negative from 4 to 12. Again, this makes sense because the volume must be increasing the entire time from 0 to 4 and then decreasing the entire time from 4 to 12. And that's the entire domain, so this must be the absolute maximum. Always conclude an optimization problem with a sentence that answers the original question. We were supposed to find the size of the cutout that will maximize the volume of the box. We conclude by saying a cutout size of 4 inches will maximize the volume of the box. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.